Welcome. So in this lecture we'll be moving to the next topic, which is the memory system. So partly this topic is quite similar to whatever we have discussed in operating system, but some of the topics may not be related, but overall it is similar. But we may be learning few algorithms, especially for mapping and page replacements, which is not something which we have discussed in operating system. Okay, fine. Let us get into the topic. So ideally, memory is expected to be fast, large, and inexpensive, so that computer can do all the work related to the memory in an effective way, and the speed can be increased, whatever it may be. But in reality, that is not the case. As the speed and the size of the memory increases, the cost also increases. Okay, that is, if you want to have a faster memory, obviously its cost will be high. And if you want to have more memory, then also you have to pay the price for that, right? So that we have discussed memory hierarchy. We'll have very less amount of cache memory. Comparatively, we'll have more main memory. Compared to that, the disk space, the hard disk space, or the space of the secondary storage will be very high. Why can't we have a very huge cache memory? Because the cost of cache memory is high. So you cannot go for a very huge cache memory, because as the size increases, the cost will increase, right? So overall, what we are going to learn here in this topic, memory subsystem, in the sense, how to create clever memory structures. So that is the job of the engineers and scientists, to design clever memory structures to improve the speed and size at a reasonable cost. Okay. So the goal is to create clever memory structures to improve the speed and size with a reasonable cost. Okay. Because generally, if you want to increase the speed and the size, then the cost will also increase proportionally. But that should not happen. Is there any way to organize memory in an effective way so that the speed and size may improve, but the cost may not improve that much? So that is our goal. Okay. So how to do that? That's what we are going to discuss in this particular topic, or in this particular chapter. So there are two ways to do this. One is by using cache memory. The other one is by using virtual memory. Okay. So we'll be discussing in length about cache memory and virtual memory in this chapter. But before that, we'll have a brief overview about memory subsystem. Let us try to understand some basic concepts about memory. Some of these you might be knowing already, but this is something like a reinforcement or refreshment. So the maximum memory that can be addressable by a typical computer is decided by its addressing scheme. So if you have a 16-bit computer with 16-bit address size, then it can address up to 2 power 16 locations, which is 64K memory locations. Okay. If you have a 32-bit address bus, then the system can refer up to 2 to the power 32 locations, which is 4G locations. If the system has 40-bit address, then it can address 2 to the power 40 locations, which is 1 tera locations. Okay. So generally, memory is byte addressable. As it is byte addressable, we say it is 64 kilobyte, 4 gigabyte, or 1 terabyte. Okay. Here the byte is not mentioned because it is generic. Generic in the sense, maybe the system may not be byte addressable, it may be something else, it may be 2 byte addressable or 4 byte addressable. Okay. But generally memories are byte addressable. In that case, If it has a 16-bit address bus size, then it can address up to 2 power 16, that is 64 kilobyte locations. With 32-bit address, it can address up to 4 GB locations. With 40-bit address, it can address up to 2 to the power 41 terabyte locations. Okay, so that is decided by the size of the address bus. Okay, for example, you might be hearing that for example, you want to upgrade your laptop. Say currently your laptop has only 4 GB memory. Okay, but you want to upgrade to 12 GB. You want to upgrade to 12 GB, and you are taking it to a computer shop to get it upgraded. But they say that no, your laptop will not support 12 GB memory. It will support only 8 GB memory. Why is it so? Why? What's the reason? If I put a 12 GB memory, why not it works? The reason is because your computer has a limited address bus size. Okay, so here you can see that with if the address bus size is 32-bit, it can address only 4 GB. Okay, so you can, from this you can calculate what would be the address size which is required to address 8 GB. Okay, so you may take this as a homework and you can try. So it means your address size is limited by some x, and it cannot access anything beyond that, beyond 2 to the power x. Okay, so that when you take it to the computer shop, they say that your system can maximum refer only 2 to the power 8 GB locations. Okay, if it is 8 GB, what should be the x value, whether it is 36 or 37 or what, you work out and find it out, right? Fine. So as we discussed, most computers are byte addressable, and some of them follow big endian format, like 68,000 processor. It's the name of a processor. It follows big endian format, that is higher order addresses are represented in lower order locations, and the lower order addresses will be specified in the higher order locations. Okay, whereas Intel processor follows little endian format. There is a processor called as ARM processor, advanced RISC. So it can be configured either way. It can be configured either to follow little endian format or to follow a big endian format. It supports both, right? Okay. So generally, memories are designed to store and retrieve data in quantities of word. Okay. So whatever you write into your word, into the memory, that we will write as an entire word, and whatever we read from the memory, that also we read as an entire word. Now what is a word? The size of a word varies from computer to computer. In some computer it can be, the word size can be 32-bit. In some computers it can be 16 bits. In some computers it can be 64 bits, whatever it may be. Okay, or else you can also say that the number of bits stored and retrieved in one access is called as word length. Okay, so the word length of a computer is nothing but whenever you try to access a memory, access means what? Whenever you perform a read operation or write operation, how many bits you read at one time, or how many bits you write at one time. So that is that is nothing but that represents the word length of the computer. Okay. For example, let us assume a byte addressable computer. The computer is byte addressable. It has 32-bit address bus. The size of the address bus is 32-bit. In that case, probably the higher order 30 bits may refer to the word. Okay, which word to be accessed. Okay, the higher order 30 bits will refer to the word which is to be accessed, and the lower order 2 bits may refer to the byte locations. Okay, so what does it mean? What do you understand by this? 32-bit address means what? 32-bit address in a sense that is it is a byte addressable with 32-bit address. So that means the word size of the computer is 32-bit. Okay, so basically it means that the word size of the computer is 32 bits. That is, each word occupies 32 bits. And again we say that it is byte addressable. So 32-bit contains how many bytes? 32 bit contains how many bytes? It contains 4 byte, right? 32, 32 by 8 is 4. Okay, so it contains 4 bytes, right? So if you take in memory, say for example, this is location 0, this is location 1, this is location 2, and this is location 3. So this is 0, 1, 2, 3. So this each location is 1 byte. Okay, each location is 1 byte. This is 1 byte, this is 1 byte, this is 1 byte, this is 1 byte. Okay, so 1 byte is what? 8 bits. So like that we have 4 bytes. 8 4s are 32. So this is what? One word. So this may be the 0th word, word 0. Okay, similarly next 4 bytes. Okay, 1, 2, 3, 4. This next 4 bytes, which is this is 4, 5, 6, 7. These 4 bytes, this may refer to the next word, first word. This may refer to the next word, first word. Okay, like that it continues, so on and so forth, right? And here what we are trying to say in the sense, if you have a 32-bit address, the higher order 30 bits may refer to the word, actual word which you want to access. The higher order 30, so this location, all these location will have address, right? Here I have given the simple address like 0, 1, 2, 3, but it may be something different also, right? So higher order 30 bits will refer to the starting address, whatever the starting address that it will refer. Okay, but this entire thing is one word. Okay, so each normally we will normally, as it said before, memory are designed to store and retrieve data in word quantities. Okay, whatever you store or retrieve, it will be in terms of word only. And here also we have discussed number of bits stored and retrieved in one access is nothing but word length. Okay, so if you read something from 0th location, actually the computer will read the entire word from 0th location to 3rd location. Okay, right? But assume that at some cases I don't want to read the entire word. I want to read only certain bytes, not the entire word. Okay, in that case we follow this scheme. That is, the higher order 30 bits will refer to the actual word which you want to read. So the starting address of the word. So in this case, if it is 00, it will refer the 000 location. And the next 2 bits will be used to refer the actual byte location. Because using 2 bits, how many locations you can refer? 4 locations you can refer. 00, 01, 10 and 11, right? So which is nothing but 0, 1, 2 and 3. Okay. So if the if the higher order 30 bit, it refers to this starting address, and if the lower order is 00, then it will refer to the 0th byte. If it is 01, it will refer to the first byte. If it is 10, it will refer to the second byte. If it is 11, it will refer to the third byte. Okay. For example, if higher order 30 bits refers to this address, then in this case 00 will refer to this address, this byte, 01 will refer to this byte, 10 will refer to this byte, and 11 will refer to this byte. Okay. So when you want to access a particular byte, then the 32-bit address can be divided something like this: the higher order 30 bit to refer the actual address, and the lower order 2 bits to refer the byte location. Okay. Right. See, when you perform a read operation, the entire word will be fetched. But assume that the processor wants only 1 byte from the word. It does not need the entire word. It needs only 1 byte. Okay. Then whatever, but actually all the other bytes from the given word also will be fetched. The entire word will be fetched. So the processor will use only the bytes that it want. It may ignore the other bytes. Okay. So when you perform read operation, the entire word will be fetched, but the processor will use only the byte it requires, and the other bytes will be ignored. Okay. Similarly, when you perform the write operation, the memory control circuitry should ensure that other bytes are not changed. Okay. So because when you perform a write operation also, the processor will refer to the entire word, not one specific byte. But the write operation may be happening on one particular byte, not the entire word. So the memory control circuitry should ensure that only that byte is changed and not any other byte is getting changed. Okay. So this we have discussed. The maximum size of the main memory is what you call, it's decided by what? It is decided by the address, the size of the address bus. Okay. Generally main memory is byte addressable. Now we'll discuss how CPU and memory communicates. Okay. So as we have discussed already, if the processor wants to read something from any memory location, it will place the address from which it to be read in the register MAR, and a read signal will be generated. Okay, and the instruction or the data from that specific memory location will be read, and it will be available in the data bus. It will be just available in the data bus. It will not get into MDR. When it will get into MDR, in the sense, once the data is available in the data bus, the MFC signal will be created at the control lines. In the control lines, one of the signal is what? MFC, memory function complete. So once this MFC signal is generated to the processor, then the processor will move the data from the data bus to MDR. Okay, and from MDR it can be moved elsewhere also. So this is the case for read operation. For write operation, if the processor wants to write something to the memory, to which address it want to write, that address will be loaded in MAR. And what data is to be written, that data will be loaded into MDR. Then it will create a write signal, write control signal. Okay, and then after few cycles, the data given here will be returned into the specific address. Okay. So for read and write, actually we have only one signal. For read and write we have only one signal. There is only one line is used. Okay. When the processor wants to perform the read operation, this line will be 1. Okay, because read is it is already in on state. There is no bar at the top. Okay. Similarly, when the processor wants to perform the write operation, this signal will be made 0, because write bar, if it is 0, this is 0 bar, it is 1. So it means that you want to perform a write operation. Okay. So if the size of the address bus is k bit, then using that you can address 2 to the power k locations, right? If the size of the MDR is n bits, then it means that the word length of the computer is n bits. Okay. And these are the typical control signals: read, write, and MFC. There can be many control signals can be added depending on the requirement. Okay. Now let us try to understand some basic terminologies related to memory. Memory access time. So this is the time between the read and the MFC signal. Okay. It is the time when you create the read and when you receive the MFC signal. MFC signal says that the data is available in the data bus and the processor can take the data. Okay. And the time between the processor generates the read signal and until it receives the MFC signal, that is called as memory access time. Okay. And then we have memory cycle time. Memory cycle time is the minimum time delay between the initiation of 2 successive read operations from in the memory. Okay. So if you take one read operation, how it happens? First the address will be loaded into MAR. Okay. Then after loading the address into MAR, it will create the read signal. Processor will create the read signal or generate the read signal. Once the read signal is generated, the data will be, it may take 1 or 2 clock cycles. The data will be fetched from the memory and it will be moved to the data bus. It will just come to the data bus. It will not even come to MDR. Okay. Once the data is available in the data bus, MFC signal will be generated by the memory controller to the processor. Okay. MFC signal will be generated, memory function complete. Once processor receives this MFC signal, it will move the data from the data bus to MDR. It will move the data from the data bus to MDR. Okay. And from MDR, the data can be moved to elsewhere, wherever it want. to that location it can be moved. This is one operation. Okay, this is one read operation. Now if there is another read operation, then again that address will be loaded into MAR and then a read should be generated. Okay, so the time delay between the initiation of two successive read. Okay, what is the time delay between creating the first read operation and the next read operation? That is called as memory cycle time. Okay, cycle time will be slightly larger than access time, of course, because access time only includes between read and MFC, but after MFC the data in the data bus should be moved to MDR. All those things are there, so that are not part of access time. Okay, so cycle time will be more than access time. And generally when we say main memory, actually we are talking about RAM. So what is a RAM? Why we call it as RAM? Why we call it as random access memory? It is a what do you call it? It is a secondary storage device. That is fine. That is, it is volatile in nature. We call it as RAM as random access memory, because any location in this memory can be accessed in fixed time. Okay, any location in this memory, any location in a RAM can be accessed in fixed time. It doesn't mean that, assume that here processor is there, it doesn't mean that processor will take less time to access this content which is here in the memory. Say this is memory, and more time to access the data at here. No, that is not the case. It can access the data anywhere in the memory in the same time. Okay, in the same amount of time or in a fixed amount of time. So that these memories are called as RAM, random access memory. Okay, whereas in contrast to this, if you take disks and tapes, they are not random accessible, they are serial accessible. You have to access location by location, track by track, or sector by sector. Okay, so they are not actually fixed, they don't have fixed access time. In case of disks or hard tapes, it does not have fixed access time. That is, if you take this as a hard disk, if the data is present somewhere here in the outer track or outer sector, that may be fetched easily, quickly. But if the data is present somewhere else in the middle of the track, it may take long time to fetch the data, because their access time is not fixed. The access time varies with respect to the locality of data, right? Okay, so this is about the basic introduction about this topic. So we will be discussing in detail about cache memory, which is used to increase the effective speed of the computer, because if there is no cache memory, then the processor will work at a very faster speed, but the memory cannot cope up with that speed. Then the processor has to wait for a long period of time. To avoid that, we introduce cache memory. So the cache memory, what it will do in the sense, the most frequently used data will be available in the cache memory, and cache memory will be very much closer to the processor. So the processor can read the frequently used data from the cache memory quickly than to get it referred from the main memory, which will be a lengthy process. Similarly, we will be discussing about virtual memory, which is used to increase the effective size of the memory. That is, it will give a feel like you have more memory than your actual capacity. Okay, fine. So there are some different types of RAM. We'll have a brief overview of that. Static RAM. So these RAMs are very fast but expensive, but they are very expensive, and also they have a complex circuit making. So increasing the size of this RAM is not that easy. That it is quite difficult, because of the complex circuit. It is impossible to pack a large number of cells on a single chip. That means increasing the size is not easy, right? Then we have dynamic RAM. Dynamic RAM, it has a simpler cell circuit, so they are less expensive, but they are significantly slower than SRAMs. Okay, their circuitry is simple, because of that they are less expensive, but with respect to the speed, they are slower than the SRAMs. Then comes magnetic tapes, which you know. So these are secondary storage device. Of course, it has very huge memory, but they are very much slower. They are very much slower. They are very much slower than the DRAMs also. Okay. So SRAMs, DRAMs are slower than SRAM, but but with respect to expense, the DRAM is cheaper than SRAM. Okay, but when you go for secondary storage device, these are less expensive, but it has very huge size. But the accessing speed will be very slow in case of magnetic disks. Okay, and this is the memory hierarchy, which we have discussed in operating system also. So at the top we have processor. Inside the processor we have register. So this is the highest level of memory. Then we have primary cache, L1 cache, which is inside the processor, and then L2 cache, which is outside the processor, then main memory, and then magnetic disk or secondary storage devices. So here if you see, the speed increases this way. It is registers. The processor can access something in the register very fastly, comparatively at a lesser speed from L1 cache, comparatively at a lesser speed from L2 cache, comparatively at a lesser speed from main memory, and it will take long time. Or the slowest device is the secondary storage device. Okay, so speed increases this way, cost also increases this way. Magnetic tapes are very cheaper. Main memory is costlier than magnetic memory. Okay, but cheaper than cache memory. Cache memory is costly than main memory. Okay, so the cost increases this way, size increases this way. Okay, because as the magnetic tape disks are less cost, you can have huge magnetic memory, huge magnetic device, magnetic secondary storage devices. Okay, similarly main memory is uh, or cheaper than cache memory, so you can have a bigger main memory than a cache memory, so the size increases this way, right? Fine. So with this introduction, let us stop this lecture. Further things we'll discuss in the next class. Thank you.